Okay, cool. Yeah. Hi everyone. Welcome to this PanGeoML working group presentation on zen3geo. So I'm excited to show you this package, this Python package which I've created a few months ago, which is designed for creating geospatial data pipelines. So yeah, you can follow the slides at this link here. I'll put it into the chat later on. But without further ado, let's get started. So I'd actually like to start off on why you should not be using zen3geo, because first of all, it is yet another GeoML library. If you think about that XKCD comic about standards, zen3geo is adding to that the choice of different standards or libraries that you can choose to use. And there are like other GeoML libraries which are probably more mature or a better fit for your use case. So it's in this presentation, I would like to clarify some of those things on whether you should or should not be using zen3geo. So stay tuned to find out. The second point is that zen3geo, it treats spatial as special. So there are some, I guess, some libraries where the spatial side is supposed to be hidden or made easy for lots of people, but zen3geo actually exposes a lot of the underlying mechanisms. So so things like projections, you need to handle that yourself. So it does require a bit of expertise, but if you know what you're doing, then it can be a good option for you to design your own custom geospatial data pipeline. And a third point that zen3geo does not have is it doesn't have any built-in data visualization tools. So it doesn't depend on things like matplotlib or PyGMT or any of those, HoloViews or any of those things. If you want to visualize things, you have to do it yourself. There is some documentation on the website on how you can visualize your spatial data. But if you want to say use something like QGIS or Matplotlib or PyGMT, it's on your side, up to you on how you want to do that. So, but say you do want to think about why zen3geo would be useful. I'll speak a little bit about the philosophy of zen3geo, I guess. It is quite a new library. It is designed to be worse than, I guess, most of the other things, but worse as in some things it does might not be correct or perfect, but it aims to be simple. So the Zen in zen3geo is an ode to the Zen of Python. So sometimes it's better to be simple than to have something that is perfect, because simplicity makes it easy for people to spot bugs and improve things the proper way. So there are some design decisions which might be bad at first glance, but it's all for the sake of simplicity. And also zen3geo subscribes to this Unix philosophy of letting each part do one thing and do it well. zen3geo, it glues together lots of different geospatial data libraries, so things like XPatcher, real XRay, data shader, etc. And all of those excel at doing what they do. And zen3geo, you can think of it as just a glue that combines all of these into a coherent data pipeline. So it's not reinventing the wheel in any sense. It's just adding something, that extra glue to make all of everything work nicely together. So yeah, that's a bit of introduction. I'll now get into, I guess, this some of the design patterns of zen3geo in relation to other GeoML libraries. So you might have heard of other libraries such as TouchGeo, EOLearn, RasterVision. zen3geo is, I guess, similar in that GeoML data space, data science space. It's designed to be a lightweight library. So unlike some of those other libraries, it has a really minimal set of dependencies, and I'll get into that in a minute. it uses a composition paradigm. So instead of using inheritance or like subclassing, it uses a compositional, like a pipe or a chain-based approach to doing things. And for its data model, zen3geo uses XRay and GeoPandas. So other libraries like EOLearn and raster vision, it does use GeoPandas as well. But for zen3geo, I guess the XRay part is the thing that sticks out. And I'll cover all of these in the following slides. But yeah, if you want to find out more about more comparisons between these libraries, you can follow this discussion link at the bottom to read more. So yeah, I'll start with I guess how how you want to install zen3geo. So you can pip install it, and it aims to it actually pulls in just two libraries, real X-ray and touch data, and so it's quite simple in a sense. And while those two libraries, like real X-ray does pull in rasterio, and touch data does pull in PyTorch, but this is the minimal set of dependencies you want to work with. And I've designed it so, because I guess like everyone has dealt with dependency hell before, when you have like a package that depends on way too many things and you run into conflicts. So this is something I've tried to make zen3geo not be make it I like to make zen3geo a bit easier to plug and play with other things you might be doing. So it relies on just these two things. And if you want anything extra, say you want to use slice raster data sets into chips, you can use pull in the xpatcher. If you want to convert, say, vector geometries into raster grids, you can use things like a data shader by pulling in the spatial extras. If you're a big fan of stack type stuff like PyStack client or StackStack, you can pull in the stack extras, and that will give you all of those. If you're working, say, with vector datasets, flat GeoBuffs, GeoJSONs, etc., you can pull in the vector extras as well, which will give you GeoPandas, PyOGR, IO. So yeah, you get the core dependencies, but any extra stuff you can handle yourself. So say, even if you just want, say, like PyStack and you don't want like StackStack, for example, you can do pip install zen3geo and PyStack. So there is that flexibility of installing just what you need and not more, not less. I'm now going to touch a bit, I guess, on a slightly complicated topic, so bear with me. So zen3geo subscribes to this paradigm of favoring it favors composition over inheritance. So what that means is that instead of subclassing some abstract base class to do that one extra thing you want to do, you would actually write your own operation, like a function instead, and then you would chain those extra things together. So what that means in practice, I'll illustrate with this example, which is this real X-ray reader, which is actually the first data pipe class I wrote in zen3geo. So given a list of geotips, so you have a source data pipe with a list of geotips, you would have an iterator that just reads each of for every file name in your list of geotips, you would pass it into your X-ray open rasterio, so you can open each X-ray data array one by one. And because it's a U function, because it's an iterator, that means you're streaming things. So you can chain this to, say, another function, and then instead of having everything in memory, it actually reads things in the stream. This is the benefit of having a chain-based approach rather than loading everything into memory. So there are lots of different data pipes available. So not just input-output readers, but also custom processors, joiners, chippers, batchers. You can find more at this API link here, which I've linked to here. And what this means in practice is, say you want to build a custom data pipe. It would be, so this is one example at the bottom here, where you can have a real X-ray reader, which reads in, say, geotips. you can have a PyOGR IO reader, which reads in, say, GeoJSON files, any vector OGR format. You can perform a series of operations on them using individual data pipes. And there is a way to connect all of those together and to build up your own data pipeline. So you can, instead of writing one big class which does all of this, you can actually write each of these parts separately and then chain them together using the composition approach. So if that doesn't make sense, you can just bear with me for a while, but this is essentially how it works. And one more thing that zen3geo uses is the X-ray data model. So rather than inventing a new data model, we've just decided to stick with X-ray. So X-ray allows for multi-dimensional data arrays, and each dimension can have a label associated with it. So you have your spatial dimensions like X and Y, and also say band dimensions. So this is an example of a Sentinel-1 GRD dataset. So not only do you have like labels associated with the coordinates, you can have attributes associated, say with the time this image was taken, the processing software, etc. So this is quite a rich data model that we'll be using a lot later on. So yeah, so that's those were a bit about the core data structures of zen3geo, which zen3geo uses. Now I'll get into a bit of some of the features that are in zen3geo. So things like spatial temporal asset catalogs, and say you have a function, and also the ease of use to extend it to your own custom function. So if you want to bring your own custom function for your particular special data set, there is a way to do that quite easily. So I'll get into that in a minute. So yeah, stacks. For those of you who don't know, stack is spatial temporal asset catalogs. So it's a standard space metadata, you can think of it. It's a JSON-based standard, which has a strong community behind it. So zen3geo implements a few stack tools, such as Stack API Search and Stack Stacker. So what this means in practice is we can, given like a list of different stack queries, so say you have a bounding box query for a particular region, you have a time range, you can set up a query for different data providers. So data providers such as Microsoft Planetary Computer, AWS, or if you have your own stack catalog, you can provide a dictionary list of queries. And PyStack, there would be a way, PyStack API searcher would process those queries and give you back a list of stack items or stack assets. So things like, I guess, geotiff files, for example. And there's a way to stack all of those together into an X-ray data array or dataset using StackStack. So what this enables is something called cloud native computing. So rather than pre-downloading your datasets, there is a way now using this stack data pipeline where you can keep the data on the cloud, write just a series of queries and data pipes, and then to connect the cloud hosted data, which is in object storage, to your compute, so your CPUs or GPUs, without like downloading anything. So you can just stream data from the cloud straight to your compute. You can find out more at this discussion link. Not every PyStack tool has been implemented yet, but there is an end-to-end workflow now available, and you can find out more at this link. Next is, I guess, on custom transforms. So there's so many types of different data sets out there, and I wouldn't I would be kidding myself if I said I've implemented everything. But so if you do have your own special data set that you want to process, the traditional way, I guess, in a lot of machine learning work is people would start with a base class of something and then subclass it to do a particular operation. So for example, this we have this example of a linear to decimal transform for a Sentinel-1 star data set. So transform logarithmic transform here. So instead of subclassing, where you have to set up all these boilerplate with like super init, self, etc., and then pass it into some transform thing, I prefer there is a way in zen3geo or torch data actually to use this a functional way approach. So you could write a simple function with just 1, 2, 3, 5 lines, and then use torch data's the map iterative data pipe to just map this function across all of your data sets. So say you have a list of Sentinel-1 geotypes and you want to process all of them from linear space to decimal space, you can just write it this way. So there are benefits, I guess, of each approach, and the benefit of the top approach is you can do things simpler, and you can do it, I guess, in the XRay space. So using XRay like label fancy indexing, whereas with torch, you kind of need to know which dimensions you're working with. So each to their own, I guess, in that sense. So that was about some of the features of zen3geo that you can do already. Those are just the basic features. And for some of, I guess, the more advanced features I'll get into, there are things such as if you want to handle, say, multiple coordinate reference systems without reprojection, or higher dimensional stuff, zen3geo also supports that. And I'll talk to you about what that means in a second. So multiple CRSs. So this is, to be honest, this is actually why I started zen3geo in the first place. I was working on this project where I had lots of Sentinel-2 scenes that span several UTM zones. And when I look at most of the other GeoML libraries, usually what they assume is that you would be reprojecting those Sentinel-2 scenes into a common projection system. Or you would need to write a very complicated you need to subclass some complicated data model for you to handle these like different UTM zones. But I did not want to reproject it because reprojecting is slow, and 2, because reprojecting distorts the pixels themselves. So I wanted to do it read in data from different UTM zones without reprojecting. And one way to do that is in torch data, you can, or zen3geo, you can pass in say a list of your geotypes. You can set up a data pipe that wraps around each of these files. You can read it in using real XRay. So these, you would read in the geotypes into an XRay data array. And once they're read into XRay, you can then slice it with XPatcher. In this case, I've sliced it into 30 chips of size 32 times 32 pixels. So you get, say, I don't know, hundreds of chips. And then with torch data, you can then batch those chips into batches of, say, size 10, and you can shuffle them. And so this is possible. So in this case, there is no reprojection done. And the cool thing is that all of this is still done with the data being in XRay. So there's no conversion from XRay to some torch tensor format. So you can still perform any number of XRay like operations on the data. And I feel like that's quite a cool feature to have if your use case depends on this. And next, also on, I guess, multiple dimensions again, I've mentioned that zen3geo uses XRay as its data model. And there's a reason for that, because XRay, you can handle any number of dimensions. You could have like a 6-dimensional array if you wanted to. But usually, I guess, most people wouldn't be working with that. Still, if you're working, say, just with something simple like a time series data set, or if you're working with like climate ocean model outputs with different data variables, XRay allows for that. So you can have, in this case, this example here shows a Sentinel-1 time series data set. So that's different time dimensions, so 15 time slices from 2020, like January to I don't know what date. And you can have different data variables or layers associated in this data cube. So the VH and VV dimensions. It also has ADN dimensions. And you can stack different layers or data variables into this data set. And once it's in this data model, you can then slice it with libraries such as XPatcher. So it's a really powerful data model that which is zen3geo natively supports. So those were, I guess, some of the advanced features that zen3geo allows you to do. I'll now give a bit of a, I guess, a roadmap on what's beyond what I'm planning beyond the current version of zen3geo, which is at v0.5 right now. So things like multi-resolution, and I'll speak a little bit on the ML library coupling side of things. So those of you working, I guess, in Earth observation or like climate modeling, you know that data sets, they don't always come in a neat box. Some of them have different spatial resolutions. And so like 10 meters, 20 meters, maybe or hundreds, 1K, 2K. And that's, it's a bit hard to handle sometimes. Most libraries, they would resample it into a common spatial resolution, but there's no reason other than convenience that you have to resample things to the same spatial resolution. So I've opened up this issue at on XPatcher on how we could potentially leverage data tree, which is this new library that handles some arbitrary a tree-like X-ray dataset thing. So I've opened up this issue, which hopefully we can handle different resolutions in XPatcher. And once we have that in XPatcher, zen3geo would be able to use that. So what this would enable is you could have super resolution machine learning models. So this is commonly done. This has been done a few times already, but most people, it seems that they implement their own way of doing things, and it would be good to have like a standardized way of doing things. Or if, say, you're working with multimodal sensors, say optical datasets, SAR datasets, gravity, or if you're working in the climate ocean space and you have different sensors with different resolutions, you want a way to combine all of those into a single, say, data tree structure. So having this feature in XPatcher would be very helpful for the wider community. And next is also, I guess, on the torch data dependency itself. So zen3geo depends on torch data. It's actually built on torch data. But torch data, if you know, depends currently on PyTorch. There is this issue on the PyTorch data repository where they're thinking of decoupling PyTorch from torch data. So once that happens, we could potentially drop the PyTorch dependency, which is quite a heavy dependency, like a gig or so. And once with that free space, you can then use up that space for other libraries such as the Rapids AI, QML libraries, or TensorFlow, JAX, etc. It's not that you can't use these currently with zen3geo. You could, but you would also be unnecessarily pulling in Torch. And if you're not using Torch, you shouldn't have to install it itself. There's nothing inherently special in Torch data that depends on PyTorch. It's just because it was built in the PyTorch ecosystem. I guess they had some, yeah, they had to connect those two somehow, but it can be decoupled. So if you're interested in that, you can follow this issue to find out more. Yeah. So next, this is my final slide. So yeah, if I guess if you're interested, you can pip install zen3geo. If you have any issues or questions, you can discuss it on our this discussion page here. And for any like new features, or if you spot a bug or something, feel free to contribute using this link. So I like to end with this quote in Chinese, which is 水涨船高弥陀佛大, which is rising water lifts our boats, and more clay makes for a bigger statue. And that's all. Thanks for having me.